Okay, let us solve this problem. This problem was asked in GATE 2014. Let us write somewhere. It says that the fuel cost functions of two power plants are plant P1, C1 is equal to 0.05 Pg1 square plus A Pg1 plus B, and for plant 2, C2 is 0.1 Pg2 square plus 3 A Pg2 plus 2B. So these are the costs of the two plants as a function of respective active power generation, where Pg1 and Pg2 are the generated powers of two plants, and these are the constants, coefficients A and B. If the two plants optimally share 1000 megawatt load, it means total demand PD is 1000, and that load is being shared by the two plants optimally, right? At incremental fuel cost of this. So optimally, sharing optimally means IC1 will be equal to IC2, and that is given as 100 rupees per megawatt hour. By observing unit itself, we can observe that this is incremental fuel cost, rupees per megawatt hour. Okay. The ratio of load shared by the plants P1 and P2 is, four options are there. Okay, I think this is also not so tough, easily can be solved. This problem falls in the category of optimal load dispatch without considering transmission losses, right? So how to solve? This is C1. So from here we may find IC1, right? IC1 is equal to dC1 upon dP1, is not it? So it will be differentiated. So 0.1 Pg1 plus A plus E. And what about IC2? Incremental fuel cost of second plant dC2 upon dP2 will be equal to, this is square, right? This is Pg1. So twice of that, 0.2 Pg2 plus 3A Pg2 Pg2 3A. This is basically P1, P2, two plants, so generations are represented by Pg1, Pg2, so better represent Pg1, Pg2. And the total load is 1000 megawatt. So PD is given as, PD is equal to 1000 demand, active power demand megawatt. It means this will be nothing but equal to Pg1 plus Pg2. Optimal loading on the two plants Pg1 and Pg2 will be equal to PD will be equal to 1000. One equation. And also it is given that for this optimal load sharing, the incremental fuel cost is 100 rupees per megawatt hour. It means it is given that IC1 given for optimal loading, we know that IC1 is equal to IC2, and this is given as 100. So we have evaluated IC1, we know IC1, this one, IC2, this one, and that is 100. So directly we may write this is equal to 100, and this will also be equal to 100. So we need to solve these equations. How many unknowns? See, one equation is here. One equation, this is one, another equation, this is third one, right? So let us solve first these two. So this is, let us say this is equation 2 and this is equation 3. It means this is equal to 100 and this is equal to again 100. So just make it 3a so that we can subtract and so that it will vanish, right? So multiply 2 with 3. Equation 2 into 3 minus equation 3. So multiply this equation with 3 so that it will be 3a. So this becomes, we have 0.3 Pg1 plus 3a will be equal to 300. And this one will be equal to, this one is 0.2 right here again. Pg2 plus 3a is equal to 100. Just subtract this so that this will get cancelled. This will be negative, negative. So tell me the value of this Pg1 and Pg2. You will get one equation in Pg1 and Pg2, and we have another equation in Pg1 and Pg2. So now two equations, two unknowns, and we have to solve Pg1 and Pg2, then take ratio of Pg1 to Pg2, right? So tell me the values.
So Pg1 is 800 megawatt.
Pg1 is coming out to be 800 megawatt, and remaining one will be 1000 minus 800, that is 200, right? So Pg2 is equal, coming out to be 200 megawatt. So the ratio will be 800 upon 200, that is equal to, okay, D will be. Any question here? This is so easy, right? So now we will solve some problems where transmission losses are also included. Any doubt till now? So you are now capable of solving any problem where transmission losses are ignored. You can dare to solve, right? Okay. So next we will solve a problem